On the surface, a standard security scan completes exactly as expected. The build passes. The pipeline outputs a green checkmark. But beneath the surface, a hidden background process is systematically reading the runner's memory, isolating and extracting every decrypted password and access credential. Because the legitimate vulnerability scanner still ran its course and threw no errors, developers had no reason to investigate. The pipeline statuses remained perfectly green. For roughly 12 hours, over 10,000 software pipelines pulled this exact code. They silently bled their core infrastructure credentials to a threat actor without triggering a single native platform alert. To understand how this happened, we have to look at the tool that was compromised, Trivy. Trivy is the industry-standard open-source vulnerability and misconfiguration scanner for containerized environments, maintained by Aqua Security. By definition, an infrastructure scanner operates from a position of absolute trust. To look for vulnerabilities, Trivy requires read access to your source code, your container registries, your AWS and GCP accounts, and your Kubernetes configurations. When you execute Trivy inside a GitHub action runner, it inherits every secret passed into that specific pipeline environment. It commands the authentication tokens required for your entire deployment mechanism. By compromising this specific defensive tool, attackers bypassed external network perimeters entirely. They turned the scanner itself into a highly privileged credential harvester, executing as an authenticated process within the build environment. The attack surface lies in how the scanner is distributed. In most pipelines, a workflow calls the setup Trivy action to download the binary, and then the Trivy action executes an entry point script based on a specific version tag, like v0.33.1. But in Git, a version tag is a mutable pointer. It is not an immutable artifact. A tag like v0.33.1 can be silently force-pushed to point to an entirely new, different commit hash. The human-readable label stays exactly the same. GitHub's user interface and archive event logs do not register tag force pushes. There is no alert, no visual diff, and no notification generated. The consequence is immediate. Any subsequent pipeline run that references the altered tag automatically pulls the new, malicious code and executes it with full privileges. The software industry relies heavily on mutable Git tags for convenience. That implicit trust creates an invisible, infinitely scalable distribution vector for malicious payloads. The group that exploited this vector is tracked by researchers as TeamPCP, operating under aliases like DeadCat-X3 and Shellforce. Historically, they targeted cloud environments for standard cryptojacking operations. Recently, their tactics evolved. They moved upstream, targeting the core build systems and release automation environments that generate software. Traditional network intrusion requires breaching one company at a time. By targeting the underlying trust mechanisms of cloud infrastructure, TeamPCP achieves exponential scale. The entire campaign stems from a single vulnerability in late February. An automated bot named hackerbot-claw found a misconfigured pull request target workflow in the Trivy repository. This is a GitHub Actions event trigger that runs workflows with elevated permissions when an external pull request is opened. A static analysis tool had actually flagged this exact workflow as vulnerable 3 months prior. The warning was ignored. The bot opened a malicious pull request. The workflow triggered, executing the attacker's code with elevated permissions. It dumped the runner's memory and exfiltrated the org repo token, a personal access token used by service accounts to authenticate with GitHub. That specific token was scoped to the entire Aqua Security organization, ignoring one warning granted an attacker write access across at least 33 different repositories and workflows. Aqua Security detected this initial breach on March 1st. They disclosed the incident and began rotating their credentials to lock the attacker out. The credential rotation was not atomic. They missed a valid service account token, leaving residual access behind. 20 days later, the attacker returned. In CI/CD environments, partial containment is not containment. Leaving a single token live turns an isolated credential theft into a persistent, cascading compromise. On March 19th, the attacker used that residual token to push forged, unsigned commits to the Trivy repository, spoofing the identities and timestamps of legitimate maintainers. They forced the pipeline to pull backdoored files from scan.aquasecurity.org, a typo squat with a swapped I and T. Simultaneously, 76 of 77 Trivy Action version tags were force-pushed to malicious scripts. Poisoned binaries were then published directly to Docker Hub, GitHub, and AWS. Out of every historical tag, only v0.35.0 was left unaffected. By weaponizing the official release automation, the attacker legitimized their malware and distributed it globally in under an hour. The payload injected into these pipelines operated in 3 stages. First, on GitHub-hosted Linux runners, it used passwordless sudo commands to bypass standard process restrictions. It executed a script that reads the memory file. This targeted the .NET runtime heap of the runner.worker process, which manages the execution of the GitHub action. The malware systematically scanned this memory block, isolating a specific JSON format. An object containing the key is secret set to true. This is the exact internal format GitHub Actions uses to hold decrypted workflow secrets. CI/CD systems must decrypt secrets into memory at runtime to use them. Any unauthorized code executing with sufficient privileges in that environment guarantees total credential compromise. For Stage 2, the collected file system secrets and memory dumps were secured using hybrid encryption. The data was encrypted with AES 256, and that key was wrapped with an embedded RSA 4096 public key. These are highly secure cryptographic algorithms, ensuring only the attacker holding the private key could decrypt the stolen data. The primary exfiltration route was straightforward. An HTTPS post request sent the encrypted bundle directly to the typo-squatted command and control domain. But if a corporate firewall blocked that domain, the malware used a fallback mechanism. It utilized the victim's own GitHub token to create a new public repository called TeamPCP docs on their account, uploading the stolen secrets as a release asset. By routing the stolen data through GitHub's own API, the attacker turned the organization's trusted infrastructure into a blind spot, successfully bypassing traditional network perimeter defenses. The blast radius expanded immediately. Among the stolen CI/CD credentials were publish tokens for NPM, the JavaScript package registry. TeamPCP weaponized these tokens to deploy a self-propagating worm, infecting 47 downstream packages. This worm utilized a decentralized command and control center hosted on an Internet Computer, or ICP, blockchain canister. The ICP is a decentralized network that hosts smart contracts, making this infrastructure highly resistant to traditional domain takedowns. When CI/CD tokens are stolen, the impact extends far beyond the initial victim. That organization becomes an unwitting distribution vector for ecosystem-wide malware. As the security community detected the March 19th attack, the threat actor actively interfered with the response. Using their compromised access, they deleted the original incident disclosure thread on the Trivy GitHub repository. When maintainers created a replacement threat, the attacker immediately deployed 47 bot accounts. Within a 12-second window, they flooded the discussion with generic praise comments to bury the technical indicators of compromise. Modern threat actors do not simply deploy their payloads and retreat. They actively wage counter-incident response operations to delay defenders and buy time for maximum data extraction. 3 days later, the attack escalated again. Forensic analysis traced activity to Argonne DevOps Manage. This was a service account acting as a bridge between Aqua Security's public open source organization and their private internal organization. On March 22nd, the attacker executed an automated 2-minute API blitz. They renamed all 44 of Aqua's internal repositories and altered their descriptions, exposing proprietary source code, internal CI/CD pipelines, and team knowledge bases. Bridging public and private organizations with a single overprivileged service account instantly converted an open-source compromise into an enterprise intellectual property breach. Throughout this entire campaign, GitHub's official user interface displayed a green immutable badge next to the compromised software releases, even as the underlying tags were silently force-pushed to completely different commit hashes. Trusting platform UI design over cryptographic verification creates a fatal blind spot for software supply chain security. To prevent this specific attack vector, engineering teams must stop referencing mutable tags. GitHub action workflows must be pinned to full 40-character SHA hashes, which cannot be silently overwritten. Furthermore, release workflows must enforce GPG-signed commits to mathematically guarantee the author's identity and block unsigned imposter commits. Finally, when a CI/CD environment is breached, token rotation must be comprehensive and atomic. Partial rotation equals zero containment. In under a month, a threat actor compromised a trusted infrastructure scanner 3 separate times, turning a tool designed to find vulnerabilities into a weapon that exploited them. If your organization ran the poisoned version tag during the 12-hour vulnerability window on March 19th, you face a severe risk of secondary compromise. The attacker systematically extracted cloud credentials and registry tokens. These stolen assets provide the threat actor with active, authenticated access inside your perimeter.